Let's see the story that potential energy diagrams can tell us. And like every story, it has a beginning and it has an end. And in this graph, I could say that the beginning could be somewhere around here and the end could be somewhere around here, right? And so the story is going to be about energy, okay? Specifically potential energy. And that's why we're keeping potential energy on our y-axis. And meanwhile, we're going to see how the reaction is going to progress through time from beginning to end. Okay? Now, if I'm going to start any reaction, I better have some reactants, right? So then what I could do is I could see these as showing reactants at the very beginning right here. That's where I would locate that term reactants. And I could actually see a little bit more. I could see that the reactants already have a certain amount of energy, right? They don't have zero energy. They have, oh, let's see, all of this energy. From zero, right, at the axis right here, and all the way to whatever this level of energy may be right here, right? So if we had numbers, we'd be able to give that a number, right? But even if we don't have numbers, we can see that they're not at zero. They have a certain amount of energy. So we could label that as the potential energy that the reactants have. So it's the potential energy of the reactants. I can put it right here, right? And then I could do the same thing for the ending of this story, right? I could see that the end is all the way over here. I also see that the reactants had a certain amount of energy, but the products also have a certain amount of energy, which seems to be different, right? It's not exactly at the same spot as at the beginning. It is lower, but they didn't end up with zero energy, and I could label that as the potential energy of the products. Okay? Now, for the rest of this line, I can tell that there has been some changes. At the beginning of this story, the reactants needed to, it seems that the reactants needed to acquire a certain amount of energy, right? They had this amount of energy, but they needed to go all the way to this amount of energy, right? And at that point, they would be considered to be ready to make products without needing any additional help or any additional energy, right? From the environment or from wherever they're getting this energy from, right? And if I think about that, then the reactants have this amount of energy right here, right? And since they bring in that much, all they would need to do is go ahead and get this amount of energy all the way to that, right? It's not all the way from the bottom, right? I don't need to go all the way here because they already contain all that amount. Only this little bit to go, that amount of energy, that has a very specific name that is pretty important, and it's called the activation energy. Okay? Now, once this reaction has, the reactants have gotten all their activation energy, they would actually make products. Oh, I forgot to actually go ahead and move the products right here. I could put them right here at the very end. There we go. Now, I was noticing before that this particular reaction is showing me reactants that had a certain amount of energy, and then when I go to see the products, they have this level of energy, whatever number that may be, but it certainly seems lower. And it is important to notice what is the difference between these two numbers, right? And if I'm gonna show that with an arrow, I could see it like right here. Or I could have turned the arrow right here or over here. So be mindful of that when you see diagrams. The important thing is that I'm really covering, right, this gap, which is really the thing that is representing the gap between the reactants and the products, right? And so that it doesn't get too crazy, I'm gonna get rid of some of these lines. There you go. And just keep the one that we did originally right here. And we're gonna call that the heat of reaction, okay? It also can be referred to as delta H, and so I'll write that along right here. It's going to be a Greek letter delta for changing heat. It's actually called delta H. And if I say delta H, or you see that term, or heat of reaction, we're talking about exactly the same thing, same exact thing. All right. Now, this thick blue line that we see that looks like the train track that we had with Thomas before is actually known as the reaction pathway. So I'll just put my term right here. And it turns out that it gives you an idea of the amount of energy that is being gained, and then the amount of energy that is then being released as we are becoming products, right? So it really gives you the idea of the changes in energy. We also saw in this lesson that catalysts do a really, really good job at lowering the activation energy of a reaction and making them go faster. That's really what they do to be able to make reactions go faster. And if we see how that could be seen in this graph, is that we would start a reaction exactly in the same place with reactants, of course, but now instead of having to acquire all of that energy that we had labeled before as the activation energy, all of a sudden we have a much lower, right, amount of energy that needs to be acquired in order to become products. The reactants are exactly the same, the products are exactly the same, so your line would start and end at the exact same spot, but now we have a path that it's way easier. It's way easier because it's like the whole reaction went on sale. All of a sudden, we have a path that only needs like this amount of energy, only up to here, right? Which is lower than what the requirement was before. And this is known as the catalyzed pathway, right? The one that I did with a dashed black line. Is the pathway that would be the energy changes when you use a catalyst. And that's why the catalyst is so good at lowering, at making a reaction go faster. It's because now it's like something going on sale. Like you wanted this pair of shoes and the whole season were $200, and then all of a sudden, at the end of the season they were like 75, and you're like, yep, let's do it. I'm gonna buy these shoes because they became way cheaper. They became a lot more doable for me to get this thing. The same thing happens with the reaction. It becomes a lot more doable when now it needs less energy. And this is how a catalyst increases the reaction rate by lowering the activation energy. The last thing that I would like to say about this reaction is that it actually has a lot to do with this term delta H, right there, right? And that actually is going to help me determine if this reaction is exothermic or endothermic, right? Exo means that it's going to release heat, and endo means that it's going to absorb heat. Now you're going to think about that in terms of the overall change in heat, change in energy of the reaction. At the beginning, we have reactants, right, with about this amount of energy, right? And at the end, we have products with this amount of energy. And we already mentioned before that this amount is lower than before, right? Reactants are at a higher point than the products are. And because of that, the reactants have more energy than the products do. So then, somewhere down the line here, there was a loss of energy. How much was that loss? That's going to be delta H, right? All of this amount was the amount of energy that the reactants lost as they became products, right? So overall, there was a loss of energy, and so then I would classify this reaction overall as an exothermic reaction. And that would be the case for any time that you see a graph that has reactants that are higher in energy than the products.